Okay, so looking at question 4 of the end of unit assessment. So we've got this circuit here, so we've got a cell and an internal resistance here, and it's being applied to an external resistance here. Now remember, this system here is being governed by this equation here, where this V here is called the terminal potential difference of the cell. So that's on your y-axis for the graph below. So if we scroll down a little bit and look at this graph, we need the V in the y position. So we need to rearrange this into this form. And I may have written it in a strange order, but there's a reason for that. So on your x-axis, we have got I. So this is your x. This is going to be your y-intercept, so the EMF. This is your y, which must mean this minus r term is the gradient of the graph there. So first, let's look at the first question down here. It says, explain why the terminal potential difference decreases as the current increases. So we can see from this equation here that EMF is constant because it's just a property of the battery you're using. You can't change the EMF of a battery, it's a constant. So you can see here that V is going to be this EMF minus this IR term. So as I gets bigger, internal resistance here, this is constant as well. So if I increases, that means that your EMF is going to have a larger and larger number subtracted from it, which means the terminal potential difference is going to go smaller. So essentially, as I gets bigger, that means this whole term here, IR, gets bigger. And because EMF's constant, that means that V is going to end up being smaller. So you get a smaller terminal potential difference. And the reason is you increase the loss across the internal resistance at higher currents. And that's the reason why that occurs. Okay, so that's that. So the next question asks you to calculate the EMF of it from your graph. So while I'm still looking at the graph, let's do that. So we can see that the EMF is your y-intercept here, and your y-intercept is at 1.52 volts. You can see there, you might need to look a little closer to work that out, but in 1.2, and you are allowed plus or minus 0.01, so there's a little bit of tolerance there to get it right. In terms of calculating the internal resistance, you need to find the gradient of this graph. So you need to pick a section, hopefully a nice long section. You need to find change in y, and you need to find change in x. And if you do that here, you end up with, what's that, 1.30 is your y coordinate. That's at, what, 0.5? And this coordinate here is at 2.5. And what's that at? It's just under, so I'd say that's probably 0.39. So that means your gradient's going to be 0.3 minus 0.39 divided by 2.5 minus 0.5, gives you an answer of 2 significant figures, and you had a tolerance, I think it was 0.44 plus or minus 0.02 ohms on this one, so you had a little bit more tolerance because of the increased difficulty in calculating the gradient precisely, so you had some tolerance, but that's how you should go about doing it. So we've answered those 2 questions here. So looking on to part C, Draw a line on the graph that shows the results from a cell with the same EMF but double the internal resistance. Well, if we remember our y equals mx plus c version of this equation, and remember that the internal resistance was the gradient of it. So you have double the internal resistance, that means you have double the gradient of the graph. So I'll just do a quick sketch over here. Originally we had this line here, so what you should have had is a line with the same y-intercept, because the EMF is the same, but it should have had double the gradient going down like that. And there were some specific points it had to go through to show that it was double the gradient. So that's that one. So there was one mark for having the same y-intercept, and there was another one for having double the gradient. The next question asks, well, what if you had the same EMF but negligible internal resistance? So if you have a look at this equation here, if R is negligible, so 0, that means the terminal potential difference is always going to be equal to the EMF, regardless of the current. So what that means is you just get a straight line going across, because V doesn't change as you change I. So you get a straight line because R is negligible, so it's 0. Okay. So part D, we've got that the current through the cell is 0.89. So we want to calculate the charge. So similar to what we had earlier. 0.89 times by 15 gives you 13 coulombs there. And there was one part was for the answer of 13, and the other mark was for the unit of coulombs. We need to calculate the energy dissipated. So we need to send it through your power, because energy per second is the same as power. You've got I squared R, which is your 0.89 squared times by your 0.455 and you should end up with an answer of 0.36 approximately watts, or something around that number. This is just the number that's quoted in the mark scheme, so something around this 0.36 to two significant figures.